Hi everyone, for part 2 at chapter 4 network day, I'm going to show you on the details of the fragmentation process at the IPv4 protocol. Okay, so we have learned before on the IPv4 packet header format as well as the IP protocol function, and now we're going to have a look at the fragmentation process. Okay, so the question is why and when fragmentation is done. We know that all the network links have the MTU. MTU is maximum transmission unit, which is the maximum amount of data that a link layer frame can carry. Okay, so not all link layer protocols can carry network layer packets of the same size. Different link types have different MTUs or maximum transmission unit. Some protocols can carry big datagrams, whereas other protocols can carry only little packets. So this large IP datagram is divided or fragmented within the network. It means that one large datagram will become several datagrams because this datagram has been splitted into smaller packets. So these datagrams will be reassembled back only at the final destination, means not at the routers. And IP header bits is used to identify order related to the fragments. Let's look at the example here where we have different routers. At the incoming link at this router, there is one latch datagram, okay, and then the outgoing link from this router have three smaller datagrams. It means that fragmentation process has occurred at this router. Okay, so these datagrams, three smaller datagrams, will be reassembled back at the final destination. So as I've said before, not all protocols can carry big datagrams. For example, Ethernet frames can carry up to 1,500 bytes of data, whereas there are some other wide area links that can carry no more than 576 bytes. So because each of IP datagram here is encapsulated within the link layer frame for transport from one router to the next router, the MTU of the link protocol places a hard limit on the length of the IP datagram. So again, like I said before, different link types has different limits on this length because it can use different link layer protocols, and each of these protocol have different MTUs. Okay, so the next one. Where should this fragmentation process is done? Okay, basically it can be done at the sender or at the intermediate routers depending on the requirement. Okay, depending on the requirement of the NTUs imposed at the outgoing link from that router. Okay, so the same datagram can be fragmented several times, okay, up until the minimum size of the fragment. And again, reassembly of the original datagram is only done at the destination host. Remember that routers should not perform this reassemble process. Okay, so this process can be done based on the requirement of the outgoing link. So if the outgoing link impose smaller MTUs than the incoming link here, so this router has to fragment the original IP datagram packets here into smaller fragments or smaller packet size. So we look into details on the maximum transmission unit or MTU. Basically, it is the limit on the maximum IP datagram size imposed by the data link protocol because of the restriction of the hardware and also software used in the network. Okay, when a datagram is encapsulated in a frame, the total size of the datagram must be less than this maximum size. This maximum size refers to MTU. So what is the size of the datagram exceeds the MTU? IP datagram is fragmented into smaller units, or it will be split into smaller units. Okay, for example, if the route here from the source to destination contains networks with different MTUs, okay, this is one of some of the examples. FDDI has 4352 bytes and Ethernet has 1500. So fragmentation process will happen where IP router here splits the datagram into several datagram. Okay, for example, from host A, okay, one datagram can has the maximum size of 4352. However, after this datagram goes to the router, the outgoing link here, which is the Ethernet link, okay, has 1500 MTUs. So this router has to split the datagram into the several datagrams so that it fits this requirement. Okay, So fragments here are reassembled back at the receiver. So moving on to the next slide. These are some of the MTUs imposed by some networks, okay, as you can see here. Okay, the most MTU is imposed by the hyperchannel, okay, which is the maximum size of the IPv4 packet. Okay, if you can see here, this shows the encapsulation process where the IP datagram here is put so that it can fit the MTU size, okay, before it is attached with the header and also the trailer. So MTU is the maximum length of data that can be encapsulated in a frame. So all these protocols have limit because of the hardware or operating system, okay, or the protocol itself, or also maybe because of the compliance with the international standard, or the desire to reduce so that it can reduce the error, okay, the reduce the size so that it can reduce the error induced retransmission. Slide. So what's actually in the fragmentation process? If you can see this is the IP header. Okay, the one that I put in the red ink here shows the IP header that are involved in the fragmentation process, which are total length in byte, identification, the flags DF and MF, as well as the fragment offset. So here we have to recall back the knowledge that we have learned from the previous lesson. Okay, identification here means the ID of the datagram, the original datagram. So if the datagram has been fragmented to different fragments, so all these fragments that comes from the original datagram need to have the same identification number. The total length is the total length of the current fragment in bytes, okay, and the flags. So remember that when DF bit is set, when I say set here means you put DF, this datagram cannot be fragmented and must be discarded or dropped if MTU is too small, okay, because this datagram needs to have it has minimum size. If an F bit is set means that if MF is equal to 1, this datagram is part of a fragment and an additional fragment will follow this one. Means that receiver have to wait until all fragments arrived at the destination or at the receiver before it can perform the reassemble process. So the next one is the fragment offset. Okay, this 13 bits field shows the relative position of this fragment with respect to the whole datagram, which is measured in unit of 8 bytes. Okay, basically it marks the position of this fragment with respect or with referred to the original datagram. To fragment a long datagram into 2 pieces, an IP module in a router must perform the task. First, okay, it has to create 2 new datagrams, okay, and copy the header field of the incoming datagram into both. Okay, and then it has to divide the incoming user data file into 2 portions. Okay, this is the example if you want to fragment a long datagram into 2 pieces. Okay, and set the data length here of the first new datagram to the length of the inserted data, and set more flag here to be equal to 1, and the offset field is unchanged, and set the data length of the second new datagram to the length of the inserted data for the second datagram. Okay, and add the length of the first data portion divided by 8 to the offset field here. Okay, and the more flag should be 0 or unchanged from original. Okay, so let's have a look at the next example. Okay, look at the fragmentation example here. So this figure gives an example in which 2 fragments here are created from an original IP datagram. In this example, the payload of the original IP datagram is a TCP segment. It consists of a TCP header, okay, and also application data. So the IP header from the original datagram here is used in both fragments, okay, with the appropriate changes to the fragmentation related fields, okay, which is the field that I have shown in the previous slide. Okay, so note that the first fragment here will contain the TCP header. Only the first segment here will contain the TCP header, which is 20 bytes here. Okay, this header will not be replicated, okay, or will not be put at the second fragment because all of the IP payload, including the TCP header, is transparent to the Internet Protocol. That is, the Internet Protocol here will not concern of the contents of the TCP header. Okay, so only TCP IP header here is put at two fragments here and not the TCP header. Okay, this TCP header is considered as the payload for the IP datagram. To reassemble a datagram, there must be a sufficient buffer space at the reassembly point. So when the fragments with the same ID here arrive at the destination, their data fields are inserted in the proper position in the buffer until the entire data field is reassembled. Okay, if you look at the example here, the first fragment here, the offset is 0. Okay, it means that it is the first segment of the original datagram. So how many segments, how can we calculate the next offset? Okay, so if you look here, the payload here is 188, okay, plus 20 header, which is equal to 208. So 208 here, you divide by 8, which is equal to 26. Okay, it means that the segment offset for the next fragment is 26. Okay, so 26. And the partial TCP payload here is the balance from 384 minus 188, which is 196. In terms of flag, okay, the first fragment here, the flag, more flag is set to equal to 1 because this is the first fragment. It means that there is another fragment will be arriving at the destination. For the second fragment here, the more flag is set equal to 0 because this is the last fragment. So when the receiver receives both of these fragments, it knows that there are no more fragments will be arriving at the, okay. The internet has a minimum MTU, okay, which is 576 bytes. It means the smallest, okay, smallest size of datagram that a router can handle for the internet. So each router must be able to fragment as needed to handle IP datagrams up to the size of the largest MTU used by the networks to which they attach. Okay. However, routers are to handle an MTU of at least 566 bytes, which is the minimum size. Okay, it cannot be fragmented smaller than this size. So this value was chosen to allow a reasonable size data block of at least 512 bytes, plus room for the standard IP header as well as options. Okay, so a common default MTU value used for IP datagrams, and even if a host is connected over a local network with an MTU larger than 576, it may choose to use an MTU value of 576 to ensure that no further fragmentation will be required by intermediate routers. Okay, so sometimes it will choose this MTU because it will ensure that other routers will not have to do the fragmentation process. Okay, so we have a look at first example of the fragmentation. There's a datagram with size of 2500 bytes that must be fragmented according to the MTU limit of 1000 bytes. Okay, so this is the first datagram of 204,000 bytes. Okay, the MTU imposed by the first link here is 4000, so it has no problem to go to this link, but somehow the outgoing link from this router has the MTU limit of 1000. Basically, again, this datagram has 2380 data, okay, when you minus the total length here with the header length here. Okay, so the first fragment here needs to have when you minus by 20 bits header, it needs to have the number that is divisible by 8, which means that you can divide this number by 8. Okay, so if you want to fragment it to 3 different fragments with the MTU 1000, you need to find a number, okay, that is divisible by 8, which is less than 1000 here. So because MTU is 1000, if you minus by header length, which is 20, the number is 980. Okay, so the largest number smaller than 980 that is divisible by 8 is 976. So this is what does it mean by divisible. Means that when you divide 976 by 8, you will get 122 without any balance. Okay. So the first fragment here will have the size of 976 plus 20 header. So the total length here is 996. Okay, notice that the identification for this first fragment is the same as the original IP datagram. The F flag is set to 0 because this fragment can be fragmented, and MF flag is set equal to 1 because this is the first fragment. It means that there are more fragments that will come following this first fragment. Okay, the fragment offset is also set to 0 because this is the first fragment. For the second fragment, it will have the same size, okay, with 976 data plus 20 header, which is equal to 996. Okay, the identification is the same as before. DF flag is equal to 0 and F flag is equal to 1 because this is not the last fragment. Okay, because when you add together 976 plus 976, okay, you will still have balance with the from the original size 2400 bytes. So it means that there are more fragments coming from these first two fragments. Okay, the fragment offset here is obtained by dividing this 976 divide by 8. Okay, so you got it. You will get 122. So this is the second fragment offset. Okay, the third fragment here will have the size of data equal to 428. Okay, so how to get this? You minus the original data size 2380 minus by 976 multiplied by 2. 976 is the data size of these first two fragments. Okay, so you get 428 and then add the header length, which is 20. So the total length of the fragment 3 is 448. The identification is still the same as before, and the F flag is set to 0 and F flag is set to 0 because this is the last fragment. There are no more fragments that come after fragment 3. Okay, so to get the third fragment size, fragment offset, okay, we know that the total length of the data for the first two fragments are 976. So you multiply by 2, okay, we get 1952. So this 1952 is the total data length for these two fragments. To get the fragment offset, we divide this number 1952 divide by 8, which is equal to 244. So this 244 is the fragment offset for the third fragment. Okay, so let's have a look at another example. Okay. Okay, so basically this page shows the summary of the previous example 1. Okay, so you can have a look here, the details on the each of the fragment size as well as the data size and also the header size. Okay, the next example here, we have a datagram with a data size of 4000 bytes, which is fragmented into 3 different fragments. Okay, so now we are not talking about header at all. So we assume that the data size is 4000 bytes. Okay, without the header. So the MTU here is not known, but the router here wants to fragment this, okay, into 3 fragments. Okay, remember that the value of the offset here is measured in units of 8 bytes. So this is done because the length of the offset field is only 13 bits long. Okay, so it cannot represent a sequence of bytes greater than 8191. Okay, so we choose the offset size so that it is divisible by 8. Okay, so the first fragment here, the offset is 0. Okay, it means that the byte here is from 0000 up until 1399. Okay, the second offset here is the size of the first one, okay, first fragment here, divide by 8. So the size of the first fragment here is 1400. You divide by 8, which is equal to 175. So this is the offset, okay, which is put into the offset field at the second fragment. Okay, so the second fragment here has bytes from 1400 until 2799. Okay, and then for the third fragment, okay, the bytes number is from 2800 up until 3999. So you want to find the offset here. We know that we have used 1400 for the first fragment, another 1400 for the second fragment. So it means that 2800 total bytes that has been put into two fragments. So these 2800 bytes divided by 8 is equal to 350. So 350 here is the offset for the third fragment. Okay, 350 here is the offset for the third fragment. So recall that 2800 bytes of data from the original data size of 4000 bytes, okay, have been put into two fragments. So the last fragments here have a size of 1200 bytes. Okay, 1200 byte. Okay. Remember that hosts or routers need to choose a fragment size so that the first byte number here is divisible by 8. So you see here the size of this fragment is 1400. The next fragment, the first byte number here, 1408, you can divide by 8 without getting any balance. Okay? The same as here, the first byte is 2800, you can divide by 8 without getting any balance. So this result from this division process is the offset number for that fragment. Okay, so this figure shows an expanded view of the fragments in the previous figure. Okay, notice that the value of the identification field, for example here, 14,567 is the ID. It is the same for all of the fragments. Okay, also the value of the offset is also shown here, 000, 175 and 350. So just now we have an IP datagram with 4000 bytes of data. So the total length here, when include with the 20 bytes header, it is assumed the header here is 20 bytes. So it is 4020. Okay, so the total here, the field here shows the total length. Okay, and this is the bytes involved with each of the fragment. Okay, so this is the flag. Okay, if you can see, this is the ID field. Okay, this is the offset. Okay, and this is the more fragment flag. Okay, the first more fragment flag is set to 1. For the second fragment, it is set to 1. The third fragment, it is set to 0. So in this example, the second fragment itself is fragmented to two other fragments, okay, of 800 bytes and also 600 bytes. So this total length here shows 800 bytes plus 20 bytes header. Okay, so we assume that the header has the minimum size of 20 bytes. So the total length here is 820. Okay, but the offset here shows the relative position of the fragments to the original data. Okay, to the original data here. Okay, and this is the offset to this data. All right. Okay, so the next we are going to review back what we have learned for today. Okay, first, a packet has arrived with n bit value of 0. So is this the first fragment, the last fragment, or a middle fragment? So do we know if the packet was fragmented? Okay, so if the m bit here is 0, it means that there are no more fragment. So to answer the second question, this is the last fragment because m bit here is set to 0. However, we cannot say if the original packet was fragmented or not. Okay, because a non-fragmented packet is also considered the last fragment. There is no indicator whether this packet is fragmented or not. Okay. Okay, let's have a look at the second question. A packet has arrived with n bit value of 1. Is this the first fragment, the last fragment, or a middle fragment? So do we know if the packet was fragmented? So the same question as number 1. However, the m here is equal to 1. So it means that there is at least one more fragment. Okay, it means that this is not the last fragment. So how do we know whether it is the first fragment or a middle fragment? Okay, the answer is we do not know if it is the first one or the middle one. Okay, we only know that it is not the last fragment. Okay, also, do we know that if the packet was fragmented? So of course, this packet was fragmented because this is the part of the fragment, because when the m bit value is set to 1, it means that there are other fragments will be arriving at the destination. So if we need to know whether this is the first fragment, last fragment, or a middle fragment, whether it is a first fragment or a middle fragment, we need to look at the fragmentation offset value. So now for your homework, you have to answer these two questions. Okay, you can submit these two questions through e-learning as a proof of your attendance, whether you want to upload your answer to e-learning or type directly to e-learning. So all the best.